I'll give a brief overview about the first unit. So, this session I'm going to give some brief about the first unit. Okay, so let's go. So I'll go to the slides and we will see somewhere. If I want to write, I will switch over the other screen and I'll write. And now I'm going to the second slide. So here in the first unit, briefly we are dealing about transmission lines and the equations related to the transmission lines, and slowly we are going to extend that concepts from transmission lines to the impedance of the transmission line, how the impedance will vary, how we have to address that impedance variations in the line, and there's some important concepts we'll be seeing throughout the discussion of transmission lines, and extension of this we will be using in the second unit. That is what you say that we will use that the matching, impedance matching. What are the techniques in the higher frequency, how to match that impedance by using the different techniques. Okay, so generally, electromagnetic waves. You have gone through some of the basic idea in the fields and waves, basically, or field theory. So there you would have studied, charges and electric charge or magnetic charge, or different laws, current law or Faraday's law, that is Ampere's law or Faraday's law, and all dealing with the fields, basically. So this is an extension of that. That is syllabus itself. You would be studying fields, and slowly you are going to the waves. So why we changing from fields to wave? In certain cases, let us go with some practical scenarios. When you see that capacitor, basically there is a charges there present. Electrostatic charge between these two plates. It's going to vary. Polarity is changes. So that is called charges, field basically happening between these two plates, and this will be applicable for even inductors. It will store that it will generate the EMF, electromagnetic force, induced EMF in the coil. So that is again a field. You can realize that there is no physical conductor connecting these two, but fields are there. We can also when moistures, the metal objects, we can also feel that some kind of electrostatic discharge, small, minute, that shocks, shock usually observes. This is all fields present, but we are not able to see it. And also there is it's not a traditional conduction where you need a wire, then only it can, what to say, you need a wire to conduct the current. Not without wire also it will, conduct. The very classic example is the lightnings. That is no need of conductor. Still, the air is allowing the fields to flow. Okay, these are the examples in the fields. The extension of this is waves. Why we need to study the waves in the electromagnetic spectrum? So when you look at everything is electromagnetic waves, starting from that what we have discussed in the last class, starting from radio waves to gamma waves. Okay, radio waves, for example, FM or ionosphere, if you want to cross that, so the signal, supposed to be in the kind of wave, so it can pass through that ionosphere and it can reach the satellite and all the different range. So basically, even light also electromagnetic signal. Okay, and UV and visible light or X-rays, so all are waves basically. So that wave we are going to use it for our transmission lines and also for designing some circuits, basically RF or high frequency. When I use that, I have to consider this electromagnetic signal is wave. So that is the idea. So we are going to see that EM waves. So basically the electrical and magnetic fields it's going to change throughout the space. While it is changing, both variation will be there through the space and also time, and requires no medium. They can travel through empty spaces. Okay, keep it in mind, that is empty spaces. Okay, so we no need exactly any wires like electricity. You need a conductor, means you need a wire, but here we don't need a wire, just an electromagnetic signal without, without a medium it can travel. And normally it is a sinusoidal waves. It's one of type, but there are different variations will be there. But for typical calculations or starting with, use it is a sinusoidal plane. I'll change the screen. Probably I'll write electromagnetic spectrum. I think you would have already saw somewhere. However, I'll rewrite it. Probably what I will do is okay, many videos coming up. Okay. I think can you see my screen? I think yeah, now it is coming up. There's a small flag is there, and to see that how it is connected. So here basically the EM signal, EM waves. Yeah. Internet works. To change to different. I think there is a lag. What I will do is I'll write it again. Okay. I think I hope it is now fine. Probably I can just increase the volume so if it is not audible. Okay. Yeah. So the electromagnetic waves. Yeah. Now it's fine. So basically, no, there is electric and magnetic field is going to change in the direction. So let us write this axis. This is my x-axis. Normally, better to write this as a axis. This is standard notation. Okay, there is a small lag. Erasing this, writing with this. This is normally, no, in the textbook. This is standard way. Normally, the direction of propagation will take it as a z-axis. Okay, this is my x. This is my y. So the electromagnetic spectrum will propagate, for example, the electric fields lines. No, let us take in this direction. This is electric field directions. That is varying with a y. So probably we can write EY. Okay, and this is perpendicular to the z-axis. The field lines will be like this, and I'll just choose other colors. Probably let us take some other color. Take this color. So this is another axis. This is no on the x plane basically. Okay, small lag is there. Okay, so parallel to the direction of propagation. So basically the electric and magnetic field is perpendicular to each other, and that is perpendicular to the direction of propagation. Okay, this is normally we write this is the magnetic field is Hx. So Hx and Ey. So normally this electric field and magnetic field will be perpendicular to each other and to the direction of propagation. This is called a typical planar electromagnetic waves or planar wave. So here there are slight phase difference will be there. For simplicity, I've written both are starting exactly at same and the exactly at same phase here. Okay, but there are practically small variations. Some 90-degree out of phase will be there, so that we will see it later. Okay, so I think I put a dot here. I think it is not visible. Okay, so it is taking a little time. Okay, I'll talk slowly. If there is any lag, you just tell me. I'll stop and I'll try to. I'm just trying to connect with the broadband. So there is some issue in the broadband. However, I'll just use it for this and try to make it things you know smooth. Let us see. Yeah, so here so when you say that electromagnetic signal, this is ey parallel perpendicular to hx. One second, I'll just so probably just mute it. We will continue with that. So the electromagnetic spectrum. Okay, just what I will do is this is okay, fine. So here the ey and hx is perpendicular to each other to the direction, perpendicular to the direction. Okay. So in more technically, what we say in that kind of wave is called transverse electromagnetic wave. Okay. So what is meant by transverse? Transverse is the perpendicular. So perpendicular to the direction, which is perpendicular, both E and M is perpendicular. So more exactly we call as this is a TM wave. So this is the general any spectrum. If you take a light, also will have the same pattern. Basically, it is like a planar wave light. So the electric and magnetic field both will be there. So basically, and so when you see that these wave, why we need to study the fields, and waves basically. So when you connect the simple circuits, for example, you have a voltage and there are some resistors, probably line resistance is connected to the battery, bulb. Let us take a bulb. Okay, the simple voltage given to the supply. It can be any circuits. So normally when the voltage is applied, what happens, there are the current conduction happen on the wire, basically that what we say vi, the voltage across that circuit and current through the circuit, and we will use all KVL KCL laws and do it. But normally what happens in the physical point of view or real time point of view, the potential whatever is between the wire actually not only on the wire, it is actually some of the voltage will be outside the wires also. Okay, so these we say as the electric fields. This is we say that electric field between these wires. Okay, so the V in the field space, the analogy is field, electric field. And current across the conductor normally we say as magnetic field. Okay, so the electric field will be between these wires, and the magnetic field will be across this wire. Okay, so this is my analogy, but this becomes the field approach of solving the circuit become tedious. So normally we do the approximation such a way that we assume only the voltage and current. We don't see it in the electric field and magnetic field, but in the real world there will be field will be there outside the wire. So that way we have to consider E and H also, because we are now operating in high frequency. Okay, so since it is high frequency, you have to consider that electric and no magnetic field. When you look this, how the waves will be, the patterns of wave will be like a TM waves basically. So the electric field lines between the wires and magnetic field across this. Okay, so we will see that basically how it is wires we call as the EM waves basically. Fine. So I'll just move into the slides. And if you have any doubt, you can just put it in the chat. I'll try to answer and try to. Okay, I'll just show that this is the EM signal. So here, what happens? All EM waves are sinusoidal, but all electromagnetic waves can be viewed as a linear superposition of sinusoidal plane waves traveling in arbitrary directions. Okay, so this is the last statement. It is kind of practically, when we say that whether all the sinusoidal waves start at the same phase. No, sometimes it will start little, late or more. So basically, the EM signal will be traveling like a sinusoid. Okay, that assumption we will make it. And what is a microwave basically? So yesterday we have seen the electromagnetic spectrum. So in this course we are more dealing about RF and microwave frequency range. So what is a microwave frequency range? Is typically from 300 megahertz to 300 gigahertz. And if you say that FM radio, it is slightly less than this. That is typically you have seen that Radio 1 or Radio Mirchi or different stations. No, normally it is 100 megahertz or 90 megahertz, something like that. Okay, 95 megahertz. So above that FM, but if you take a VHF band, very high frequency or ultra high frequency or cable TV, that frequency, or if you go to the mobile phones, for example, 2.5 or 3G, 4G, all fall into this 2 to 5 gigahertz band. Okay, so that band of frequency also called microwave frequency, and this microwave frequency can be extended till 300 gigahertz. Okay, so why it's called microwave? So we could have given some other name. The name comes because when you say that frequency, when you convert into the wavelength, let us take 300 megahertz to 300 gigahertz, typical some value, let us take 100 gigahertz. Typically we'll take, okay, let us take realistically, let us take 30 gigahertz, let us see. Okay, so if I take 30 gigahertz, what is the wavelength? Probably I'm trying to use that, yeah, pen. What is that? Let us take frequency is 30. I think you can see my screen. If anything is there, you put it in the chat. I will try to
One
see that
centimeter.
what. Yeah. So here, 30 gigahertz. Let us take the frequency. Okay. So what is a wavelength? Basically, the wavelength can be measured from C by F. Okay. So C, I'm going to write in terms of centimeters. 3 into 10 to the power of 10. If it is a meter, 3 into 10 to the power of 8. Since it is a centimeter, 10 to the power of 10. And frequency is 30. What is a G? G is gigahertz at 10 to the power of 9. So, numerator 30. So, what happens? I will get 1 centimeter. Okay. Typically 1 centimeters. And if it is a 300 means typically I'll get 10, what you say here, I'll get Is that correct? Yeah, fine. So if it is a 300 G, this becomes a 0.1 centimeter. Okay, then it is not ended, it is can further extended. So basically it is more than millimeter waves. Okay, more than millimeter. Basically it can go till microcentimeter or micrometer also, right? This is typically, if you go to 0.01, let us, if you further down the wavelength, so this can be written as typically how much, 1 into 10 to the power of minus 2. And if you want to convert into meter, typically minus 2, no, again. So typically 10 to the power of minus 4 meter. So it is going into the range of micrometers, right? So that is a nomenclature basically, because it's the wavelength is approaching close to micro, so we call as a microwaves. Okay, so another name is millimeter waves also they may call, but in general, so microwave is to deals with the wavelength is coming very smaller and smaller, so that there's a broad range frequency also called the microwave. Okay, that is the reason. So sometimes these frequency band is called RF, because this is for radio communications. We have used it, no, sometimes this frequency, not exactly 300, less than 300. Okay, so broadly we say RF and microwave frequency. Okay, so if you see that last point, whatever I tried to tell in the last slide, so the field components will be that no, just proportional to the direction of propagation. So it's called the transfer electromagnetic waves. Okay, so this is, I feel this is something important. You should realize that what happens at higher frequency. So if you have any doubt after seeing this diagram, you can just stop and ask me and put the question in the chat. The physical length of the conductor basically. Okay, so the physical length of the conductor is something a deciding factor for higher frequencies. That is more important. Just I put a double line in that physical length. Okay, so the physical length means what? L here. Okay, this is my physical length. So when we see the conventional circuits, whatever you have studied, analog or digital or mixed mode or and all, it's fine. And when you're going to the RF frequency range, whatever circuits I'm going to use it, that physical length of higher frequency circuits, what happens? So that I have to see, I have to compare with the wavelength of the signal, what signal I'm going to operate. So if you see that in this typically 1 kilohertz to 100 kilohertz, if you see that wavelength, let us take for a simple easier calculation, I'm going to take 300 kilohertz. Okay, 300 kilohertz. So what is the wavelength? Can you put it in the chat? I'm going to take 300 kilohertz as my operating frequency for my circuit. This typically, this is a wireline. These are low frequency wireline communications. We will use that. If I take the frequency is 300 kilohertz, what is my wavelength? I'm going to say the chat. One centimeter. That is for a last question, right? Anirudh. For this, what is the wavelength? 300 kilohertz. What is the wavelength? Or you can take 30 kilohertz. Let us take two values. So you can just put the wavelength for two frequency, 30 kilohertz and 300 kilohertz. You can, this is, you just name it as a lambda 1. I'm just writing here. This is my lambda 1. This is lambda 2. So what is the lambda 1 and lambda 2? Are you getting? What is these two values? Lambda 2 is 10 kilometers. Fine. Very good. Lambda 1 is typically 100, no? I think so. 100 kilometers. Because typically it is how much? 100 kilometers, right? So because there is one more zero will be there in the denominator. I think no, the frequency will be less, so that numerator will be higher. You get typically 100 kilometers for lambda 1. Lambda 2 will be 10 kilometers. I think so. So lambda 1 is 1 kilometer, lambda 2 is 10 kilometer. Is that so? Lambda 1 is 30 kilohertz. For 30 kilohertz, 10 kilometer. No, 1 kilometer you have written. Lambda 2 for 300. Lambda 2 for 300 kilohertz. How much? Let us calculate. So lambda 2 is nothing but C divided by F2. So F2 is, let us take in terms of meters only. That is not a problem. This is lower frequency, no? 300 10 to the power of 8. And F2 is 300K. 3 into 10 to the power of, this is K is 3. Again 2 zeros is there. So 5. So this is 1 into 10 to the power of 3. So 1000 meters. So 1000 meters, 1 kilometer. Okay, very good. This is 1 kilometer. What is that? 30 lambda 1. 3 into 10 to the power of 8 divided by, this is 30 into 10 to the power of 3. Okay. So how much? So this is 30. 30 will be cancelled out. This is 30. This is 7 will be there. So 10 to the power of 4. Okay. So we will get 10 kilometers. Correct. So lambda 1 is 10 kilometers. Lambda 2 is 1 kilometer. Okay. So lambda, okay, for 30 kilohertz is 10 kilometers. Correct. And 300 K, the lambda 2 will be 1 kilometer. Correct. So what happens basically when I'll just erase everything and just put the values here. Probably I'll just go to this here. Erase all. And I've taken a 2 frequency, that is 130K, and here taking 300K. Okay. So 30K I got, when frequency is less, the wavelength will be higher. So it is 10 kilometer. This is for 300K. So the wavelength will be 1 kilometers. So similarly, whenever frequency is increasing, what happens to that? The wavelength is coming down. So wavelength is, when it going this side, wavelength is coming down very drastically. Okay. So what happens if the frequency is increasing? The wavelength is coming down. Okay. So when the wavelength is coming down, when it is comparable to the physical length, so now we are in the range of microwave engineering, microwave domain.